warm-up, we'll start with the current slide and go from here. Here we are. Okay, just a couple of announcements. Don't think anything's too major now. First, what was the meeting of the math team? Did you get to it? What's that? Oh, sorry.
I ended up at high school. When I put in my GPS, I remember how to get back. But I just want to put in my GPS. Long story short, I ended up at a high school.
I see.
High school or something.
Yeah, Winona High School is right next to it. Right. Okay. So, well, anyway, the math teams, I think, are up and running now. I think we have 3 teams of 4 people each. If anyone still wants to participate, I think one of the, can I get your name, please? No. Serenity, got it. I think one of the people yesterday they had counted on coming said that he couldn't do it, so we may have a vacancy, so if anyone is interested in participating, and even if you don't want to go to the competition, or you can't go because you're working or something like that, it's a Saturday, October 6th or sometime in there. I can't go because we're going to be out of town. But if you can't go, you still, I think, would benefit greatly. It's fun, it's relaxed, it's the practices we have, and I hope we'll get started Monday, Wednesday afternoons, 3:15 to 4:45, but we may not go that long. But any time in that time frame, you can come by and have it. I think it will be beneficial in future courses as well. And the other things, this won't really affect my office hours any, but I do have a meeting on Friday, normally on Friday on the Birmingham campus. I'm there 7:45 to 11:45. I'll be there longer Friday because they've called a meeting for 12:30. But that won't affect my office hours. But if you were trying to catch me, I'm going to be in the meeting from 12:30 until whenever it's over. And when it's over, I'm going home. So so anyway, I will be there up until 12:30. So it will actually extend my office hours a little bit. All right. Any questions on anything? Sorry about my voice. I went to the UAB game Saturday, so I yelled too much. Sorry about that. So anyway, any questions on anything we've covered so far? All right. We were going through what they call the parent functions, the most general forms of all these functions. Had we started on the squaring function, or this is where we're going to start today? We had started. Okay? Did we get most of this covered? Okay? Did I ask you what this shape is called? Parabola. Very good. Okay. And we talked about its whether it's even or odd. Even, exactly, because it reflects across the y-axis. Okay. All right. So, any questions about that? Decreasing the first half, increasing the second half. Okay. Symmetric about the y-axis, that's the same as being even. So that's and the other. Relative minimum at 0, 0. All right. Any questions on the squaring function? I think you're probably fairly familiar with it. And a lot of the next section will, I believe it is, will deal with quadratics. Okay? No, I'm sorry. Next chapter. Okay. 2.1. All right. All right. Now we're moving to the cubic, square root, and reciprocal functions. The others we see quite frequently. These we don't see as much, but we see them often enough that we need to pay attention. Okay. Here are the first on the cubic function. Okay. Here is the parent function of all cubic functions, mother of all cubic functions. F of x is equal to x cubed. Okay? Now, anyone know right off the top how it looks? We're going to get that on the next slide. Okay, now the cubic function starts low, goes high, and goes up. Okay? What is its domain? All real numbers. All polynomial functions have domains of all real numbers. How about its range? All real numbers, because if you cube a negative, you get a negative. Cube a positive, you get a positive. So since all real numbers can go in for x, all real numbers can come out for your y or your f of x. Okay? What? Even or odd? Odd, because whatever it does this side, it does the opposite that side. Can I get your name, please? Sandra? Okay. There you are. All right, anyone else come in since I called roll? Okay? Now, does it have any intercepts? X-intercept? Second? Yeah, 0, 0. Intercept always an ordered pair. That's the x-intercept and the y-intercept at the origin. 0, 0. Okay? And guess what? Increasing, decreasing. Always increasing, exactly. Even down here where it looks like it might flatten out a little bit, never does. You pick something just a little bit short of 0, like a negative 0.1, cube that, you get negative 0.001, okay? So it's very close to 0, but not. And a little bit to the right of 0, like 0.1, it'd be positive 0.001. So yeah, that's why it looks to flatten out, but never gets completely flat. So it is always increasing ever so slowly there. Okay? Symmetric about the origin, that's the same as saying what we said earlier, an odd function. Symmetric about the origin means it's an odd function. There's the graph of it. Now, will all cubic functions look like this? Generally, no. Most cubic functions will start one direction or the other. We'll start them this way, go up, and quite often have a relative maximum here, go down and have a relative minimum, and then go up. That's more characteristic of what most of your cubic functions will look like. This is just a parent function where those max and min are just sort of collided at 0, 0, and you start to have a max, and then you carry on like it was a min. Okay. Now, square root function. Okay, domain. Zero to positive infinity. You cannot take the square root of a negative number. Not in the real number system. Okay? Range of the square root function. 0 to infinity again, because this is called the principal square root. You could have a negative in front that allows it to go negative, but without the minus sign in front, this is always positive. Okay, even or odd? Neither, because it's not doing anything on the other side of the y-axis, on the other side of the origin. It's only on in the first quadrant. Okay, so it can't be even or odd. Okay, let's see what else. Does it have an intercept? 0, 0. Okay, just like before. And how about is increasing, decreasing this? Increasing everywhere it's defined from 0 to positive infinity, always increasing. Make sense? Okay, here's what it looks like. What does that sort of look like to you? What's that? Okay, exactly. Half of a sleeping parabola, right? Okay, because it's down on the side, 1/2. Why don't we have a whole parabola there? It would not be a function because it would fail the vertical line test. So yes, you can only have half of it. Now, if you put the minus sign in front, like I was suggesting before, you lose this, and then you have that part, but you can't have both. Would not be a function anymore. Okay? Any questions on the square root function? Now, it can be later. We'll talk about. In fact, the next section starts talking about how we change functions, shifting them, transforming them. Okay? And that can happen. We'll get that in the next section. And then the reciprocal function, 1 over x, f of x, 1 over x. How about its domain? Everything but zero. All real numbers except zero. You cannot divide ever by zero. How about its range? Everything but zero as well. Now, here's part of the reason for that. The only way this thing could be zero is that the numerator were allowed to be zero. That numerator is a 1. It's never a 0, so you cannot ever get the function itself to be a 0. So it's all things, all values, all real numbers except 0. Okay? And here's how they express it. This is an interval notation. Negative infinity up to 0. This is the domain. Not counting 0, union that with everything from 0 to the right. Again, not counting 0. Same thing for the range. Everything from negative infinity up to 0, but not counting 0, and then from 0, but not counting it, up to positive infinity. Okay? These look identical, don't they? Are they the same? Say again? Say again? I couldn't hear.
What you talking about the same?
They look identical. Are they the same? One's talking about the domain, one's talking about the range. So that's the difference. What else is different about it? It has to do with that. Yes, this was talking about the horizontal axis, that was talking about the vertical axis. So they're talking about completely different values. These, the way we've been talking with that, these would be x values, these would be y values. Okay, how about even or oddness? They're odd functions, because whatever you do for a positive x, when you go to negative x, it does the opposite. Okay, so it's an odd function. What else could that tell you? Reflective. Origin, yes. That's the same thing as saying symmetric without the origin. These two statements are equivalent. Okay, how about its intercepts? No intercepts at all. We already said x can't be 0. That means there could be no y-intercept. And we said y can't be 0. That means there can be no x-intercepts as well. So does not have any intercepts. That basically goes from there too. And it's symmetric with respect to the origin. Here's how it looks. This is f of x equal 1 over x. As x gets closer to 0 from the left, the f of x goes infinitely high. As x gets farther from 0 to the right, the f of x is getting closer to 0. If you go to negative numbers, 1 over negative numbers, always going to be negative. So here you are in the third quadrant. The further you get from the origin, the closer you get to 0 from the negative side. And the closer you get to 0, the closer you're getting to negative infinity, whatever that is. So that's how the reciprocal function looks. A lot of times we'll just look at that and say that's a reciprocal function, but it always has a matched pair. Odd, symmetric about the origin. Okay. Now let's look at this last group, step and piecewise defined functions. We've already dealt a little bit with piecewise. I think this is the first time we've hit step functions. Okay? Functions whose graph resembles a set of stair steps called step functions. Very clever name. Okay? The most famous, it's really famous, of these step functions is the greatest integer function. And here's the symbol for it. Very seldom is it used. I found that it's used, but it can be. Greatest integer in x. That's how you read it. So f of x is equal to greatest integer in x. Now it's kind of a double bracket. You know, an absolute value is a single bracket. This is a double bracket with sort of a close on it. Okay? Absolute value is 2 lines. This is sort of like an absolute value in here with a bracket on the outside, or something like that. And that means the greatest integer less than or equal to x. That's what that means. Can I get your name, please?
Trey Stevens.
Say again?
Trey Stevens.
Okay, Trey. All right. Anyone else come in since I called roll? All right. So let's try a few of these. What does that mean? Read it for me. And what would that be? Say again? -1 is equal to -1. The greatest integer less than or equal to -1. How about -1/2? That greatest integer is -1/2. Say again? Yes. What would that be? No, that's not an integer. -1, you're absolutely right. So, -1, you go down -1, -1/2, you go down -1. So that's why, until you get to 0, then you step up there, and then you step up there. So that's why it's called a step function. Let's do a few more. Greatest integer, read it for me. And what would that be? 0. How about this one? 1. How about this one? 1. Okay. For positive numbers, they're pretty easy. Okay? Especially if you write them as a decimal form, you just drop the decimal. That would be the greatest integer in that. It's when you go on the negative side that you have to think greatest integer less than or equal to. If you drop the minus sign for negative, you're going to something greater than, not less than. So you just have to flip it around for that. Okay, so here are some of the characteristics. What do you reckon the domain of that function is? Say again? That's the range. Not quite close. Huh? All real numbers. Domain is all real numbers. Now the range. Second? Okay, not quite. Whole numbers are restricted to positive. It's in the name of the function. Integers! Okay, the greatest integer in, it would be all integers. Very good. Domain is a set of all real numbers, but the range is a set of all integers. Okay, interesting kind of look to it, because it's the greatest integer less than or equal to. So for all these down here between -4 and -3, -4 is the greatest integer less than or equal to that until you get to -3, then you jump up here. And then all integers, all numbers in here, the greatest integer less than or equal to any of these numbers is -3. So you use this one until you get to -2, and then it jumps up to -2. Then the what? Then the 0. So that's why it's called a step function. You can see this one up like that. Okay? We hit domain and range. How about intercepts? Any x-intercepts? What? Okay. It goes from 0, including 0, up to 1, but not including 1. So that would be the x-intercept. How about y-intercepts? 0, 0 is all she wrote, because you can't have more than one. You can have more than one x-intercept, okay? But you can't have more than one y-intercept. Why? It would fail the vertical line test, because the y-axis is a vertical line. You can't have but one. You may not have one, but you can't have more than one, okay? Let's see. How about symmetric? Is it? It kind of looks like that, but not quite. Because if you go slightly negative here, you're down here, slightly positive here, you start there. So no, it's not symmetric about anything. So is it even or odd? Neither. It's a neither function, because it's not symmetric about either the origin or the y-axis. Okay. Range is a set of all integers. The graph has a y-intercept at 0, 0, and x-intercept everywhere on the interval 0 to 1, counting 0 but not counting 1. The graph is constant between each pair of, oh yeah, is it increasing or decreasing?
It's always increasing.
Okay. It's constant between the integers and then jumps up to the next integer. So I guess you call that increasing at the integers, but constant in between the integers. So we don't really talk too much about that, but never decreasing, we can say that. Okay. All right. So it's constant between each pair of consecutive integers of x and jumps vertically 1 unit at each integer. Okay. Later, you will start calling this a discontinuous function because it's not, you can't get from every point to another point without lifting your pen off the paper. Okay. It's not a continuous function. We're not calling it that yet, but we will later. Okay. Now, let's do a few evaluations of it. I've got to get my pen extracted here. And why is it not coming up? There we go, finally. It's not responding. There we go. It's very, very slow this morning. Okay, there we go. All right, evaluate the function when x equals -1. So f of -1 is the greatest integer in -1 plus 1. What is the greatest? I said -1 and wrote an x, okay? What is the greatest integer in -1? -1 plus 1 is 0. Very good. What is f of 2? Greatest integer in 2 plus 1. What's the greatest integer in 2? Say again? 2 plus 1 is? Didn't know you'd be doing such high-level math this morning, did you? Okay. All right. How about f of 3/2? Greatest integer in 3/2 plus 1, and this would be 1 plus 1. Even higher level math, right? All right, you're getting your money's worth today, aren't you? 1 plus 1 is 2. Everybody remember that. Okay, good deal. All right, that wasn't too bad, was it? Let's clear that out of the way. And let's see how they do it. Okay? For x equals -1, the greatest integer less than or equal to -1 is -1. So f of -1 is greatest integer -1 plus 1. They sure can say it a long way, can't they? -1 plus 1, which of course is 0. And for 2, just like you said, that's 2 plus 1, and that's 3. And for 3/2, it's greatest integer less than or equal to 3/2 is 1. You could write that as 1 1/2. Drop the half part and keep the integer part. If it's positive, you can do that. That's 1, so 1 plus 1 is in pre-calculus 2. Okay. What's that? Okay, what if that were a -3/2? What would be the greatest integer? Say that? It's what? It's a -1 1/2, and what is its greatest integer? Less. -1's to the right of it. Picture it on the number line. Here's -1, here's -2, here's -1 1/2. What's the greatest integer less than or equal to -3/2? -2. You have to always look to the left. -2. So you can't drop, for negative numbers, you can't drop the decimal, and you can't drop the fractional form when you write it as mixed numbers. You have to always look to the left, and it goes that way. For positive numbers, that's all you do. Drop the decimal or drop the fractional part, and you have the greatest integer. Those negatives throw you off by 1. Make sense? Does that answer? Okay. All right. Now, does this look a lot like we had before? Looks like it, but it's not quite. Before, yeah, this was down here, this was down here, this was because what have we done? We took the greatest integer function and added 1 to it. So everything got lifted by 1. Everything got lifted by 1. Okay? So that's what it looks like. Still a step function. Okay? It just, the graph is not quite the same. Make sense? Okay? Now, there is a checkpoint. Please do your checkpoints. Okay? They're skipping example 3, which is a shame. Okay. Let's clear this out of the way and do example 3 because greatest integer functions are not the only piecewise defined functions. Here's another one. Sketch the graph of f of x is equal to a single brace, and it's 2x plus 3 for all x's less than or equal to 1, and it's minus x plus 4 for all x's greater than 1. Okay. And it said sketch the graph. It doesn't say do anything else, just sketch the graph. So I'm going to draw the graph, draw a and axes, 1, 2, 3, 4, 5, 6, negative 1, 2, 3, 4, 5, 6, positive 1, 2, 3, 4, 5, negative 1, 2, 3. Pretty ugly graph, but anyway, get over it. All right. How do we go about graphing that? When you were in lower level math, how did you do graphs? What was your favorite technique? Okay. Okay. Say again? What were you going to say? Okay. And that's not a bad idea either. I thought someone was going to say do they call it T-table or something like that? Yeah, but y'all are already jumping past that. You're doing it, you're just not doing it. He said, go for 0. I can tell he's lazy, okay? Choose the easiest number to put in there, okay? So put a 0. But before you do anything else, if you choose x equals 0, what does that mean you have to determine first? You have to figure out where you are, Waldo, right? Where are you if x is equal to 0? The upper one. There you are. You're not down here because 0 is not greater than 1. It's less than or equal to 1. So you use this one. So x equals 0, and what would you have? Second? 3. Okay. There we have 0, 3. Okay. Give me another x. I feel like a cheerleader now. Give me an x. Okay. Huh? 3. Okay. Where are you, Waldo? You're at the bottom because 3 is greater than 1. And then you plug it in here, and what do you get? Say again? 1. Okay, so at 3 you get 1. Okay? Got 2 points. Can you draw it from there? Need a few more. Negative what? 3. Okay, negative 3. Where are you, Waldo? You're on the top one because negative 3 is less than 1. Okay? What will that give you? Negative 3. So at negative 3, you're at negative 3. Okay, you're down here. Say again? I can't hear you. You can start graphing. I know from here it's going to be doing this. Okay? But I don't know where, I know I can keep going here as far as I want to. I don't know how far to go there. So I think I need another point or 2. 2. Okay, let's use 2. Where are you, Waldo? Bottom. And what would that give you? 2. 2, 2. Y'all like these ordered pairs, don't you? Okay, 2, 2. Okay, I still don't, we can do some graph here. I know from here on, it's going down like this. I probably missed that point, but close. Yeah. Negative 4 0 would be on it. And, no, I'm sorry. 4 0 would be on it, so I missed that one. But I came close. Okay. We still got that gap in there. Oh, let's do 1. Where are you, Waldo? You're at the top because it's equal to 1. And what would that be? 5. Oh, is it? Yeah. Yeah, 5. I don't have that plotted too well here, but somewhere like there. There we go. Now, I know that one ends right there because that's as far as x can go on this side. Okay? But that one doesn't start at 2. Where does it start? It starts just past 1, but not 1. Okay? Oh, you need to put a circle. So go on and put a 1 in here, understanding it can't be there, but it goes up to there. So what happens if you put a 1 down here? 3. Okay? But at that 1 and 3, I'm going to put an open circle. Okay? And then I can go on down here. Okay? This is a closed circle. That means it terminates there. The other side, it has to be an open circle because it can't be at both places. So that one is defined there. This one's not. But everywhere to the right of that, it is defined. So don't start here. Start at that number that you're looking at, a open circle, wherever you have the strict inequality. Does that make sense? Okay. And does this look reasonable? Yeah, this side, that's a linear function with a slope of 2 and a y-intercept, which you were going to say, of 3. So yes, that makes sense there. Over here, you have a -1 slope, and sure enough, that's what it looks like there. If you had a y-intercept, if it could extend it to x equals 0, it would be at +4, but it never gets there. Okay? So yeah, that's how it looks. Make sense? Okay. Piecewise defined functions are usually not that miserable to graph, but you have to be fairly careful, especially at that point of discontinuity. Okay? And sometimes it's not discontinuous, but that's where you have to be careful. And because it's so important, they do give you a checkpoint. So please pay attention to that. I'd say do it as soon as you can. Let's erase my chicken scratch and see how they do it. Okay? Oh, they don't do it. That's right. They skipped this one. All right. So let's go back and review our parent functions. What's this one called? Constant function. Okay? And we know all the characteristics of it, right? Okay, good. How about this one? Do what? Do what? You can't read my hands? No, what? The identity function. Okay? How about this one? Absolute value function. Okay, how about this one? Square root function. They aren't doing them in the same order they did in the text. How about this one? Squaring function, also called a quadratic, by the way. That's a cubic function. Reciprocal function. Is a piecewise function, what is the name of that one? Greatest integer function. Very good. Okay? Now, there are other stepwise functions I think use a lot more, even though they say greatest integer is the most famous. Any of you ever mailed a letter? Okay? How do you determine what postage to put on? Yes, how much it weighs. And if you went to the post office, you could probably find the graph. I don't even know what a first-class letter is now. 48.52, I don't know. Whatever, I use a forever stamp, so I don't even know when I ever mail. I hardly ever mail anymore. Okay, but whatever that is, from 0 to 1 ounce is that amount, whatever that amount is. Now, 0 ounces, I've never mailed a letter at 0 ounces. Right? It's not there. Okay? So it has the open circle at 0. But then at 1 ounce, I will still do the 40. So it's open circles on the left, right, and it's at 44. And then you go to 1 to 2 ounces, you jump up to the next one, 2 to 3, okay? That's a stepwise function. To me, that's a lot more famous than the greatest integer function, okay? Some of you, originally when they came out, there were a lot of these. I don't think there's many of them anymore. But there's some of you on your phone things have that. If you do so many minutes, it's this price, and so many other minutes, it got up with this and that. Okay, if you have that, that's a piecewise defined function. That's a step function because anything between 100 minutes and 200 minutes is going to be the same rate. Then when you go to the next level, it goes to a different rate. You do the same with data. Yeah, all those are piecewise defined functions. Okay, many of them are step functions. Now, if it's price per minute and the rate goes up, then it's slanted and the rate gets steeper. Okay, so that's a different issue. Okay, but anyway, those are all piecewise defined functions. I think we're more famous than greatest integer, but I won't make a big deal about it. So familiarity with these simple graphs will help you analyze the shape of more complicated graphs. In particular, get this, graphs obtained from these graphs by rigid and non-rigid transformations. We haven't run into that before, have we? Guess what the next section is? Rigid, transformations. So we're going there very soon, but let's first do our vocabulary. All right. Now, it helps if you have your books open. Okay? You see that first thing there? It says in exercises 1 through 9, match each function with its name. Alpha of x equals that funny symbol around an x. What's that one called? The greatest integer function, that's g. Number 2. Say again? That's alpha of x equals x. What do you call that one? Identity function, that's I. Okay? Number 3. Alpha of x equals 1 over x. Reciprocal function, that's h. Okay? Number 4. Alpha of x is equal to x with a little 2. Okay, quadratic. Is that on here? I don't see it. It's a squaring function. That's number 8. You see that? You don't have vocabulary?
No, we don't have it like that.
Oh, you don't?
We have like 1 through 9, but there's not.
Oh, wait, I'm in the wrong book. I'm sorry. Where is my other book? I may have left it right there at the doctor's book. I usually keep it. I don't know. Don't have it. Sorry. I didn't bring it in. I don't know. I hope I didn't lose it. Okay. Okay, y'all don't have the. Okay, what do you have? Oh, you don't have the choices.
Yeah.
You just name them. But they're the same names, right? Oh, okay. No wonder y'all weren't answering too well. Okay. What do we call, was it 4? Squaring function or quadratic. Either will do. Number 5? Square root function. Number 6? Take a constant function. Number 7? Absolute value. Number 8? Cubic. And number 9? Woo, we didn't do that. Say again? Linear function, absolutely. Okay. Number 10, fill in the blank. The constant function and the identity function are 2 special types of blank functions. Linear functions, you're absolutely right. Okay, homework exercises here. I get close enough to my computer, so you'll pick it up. Either 11 or 13 or both. Any of the odds 15 to 25, either 27 or 29 or both, either 31 or 33 or both. Any of the odds 35 to 39, do 41. Then any of the odds 43 through 45, either 43 or 45 or both. Okay? True, false, you won't see many of those on the test or anything, but it's still not a bad idea to think through those. All right, guess where we're going to go now? 1.7. Okay. And while 1.7 is coming up, let me give you your quizzes. Okay? Say again? Quiz, yeah. These are take-home quizzes, and 10 questions, pretty simple. There's one, number 10 requires graphing. Some of the others you may want to graph to get your answer, but you only have to do one. So that's number 10. So if you need graph paper, let me know. I'll give you graph paper. If you have your own you'd rather use, you're more familiar with, use that. Need graph paper? You have graph paper. How about you? How about you? You have graph paper? Okay. Okay. How about? You have graph paper? Did I give someone a trig test? Okay, you don't get the trig test. Don't be taking my trig test, okay? Did I give anyone else something that wasn't a graph paper? Okay. You did a graph paper. You did a graph paper. Did I give you got it. You know what? I put 29 and she gave me 20. So I'm going to have to run more copies. Sorry. Let me make sure I don't have any extras here. No, I don't. So I think I need 9 more of these. And how many of you need graph paper? Nine more. Mine needs some graph paper. I'll make it later. I need 9 more of these, so I'll be right back. Sorry about that. Well, you did get one right after class. Okay. Sorry about that. She just misread my number. It said 29, and I think she read it as 20. All right. I guess I should have counted, but most of the time she gets it right. All right, we're continuing Chapter 1, Functions in the Graph. Now we're going to be talking 1.7, Transformations of Functions. The first few of these I think you'll find pretty easy. Then we'll do some that you haven't hit before. We'll do vertical and horizontal shifts to sketch graphs of functions. Then we'll use reflections to sketch graphs of functions. and we'll use non-rigid transformations to sketch the graphs of functions. So 3 different ways we're going to transform functions. Let's talk about those shifting graphs. Okay? Many functions have graphs that are transformations of the parent graphs. Okay? So we're going to go talk about parents first and then go from there. This one looks a lot like a parent function. What parent function would you use? The squaring function. So they go and draw the squaring function here. Now what's different from this and the normal squaring function? You added 2 to what? To the y, to the function value itself. The squaring function is x squared. You added 2 to that, which was to the y, which means you go up 2. Okay? Just don't say yours. Okay. Go up to here, go up to there, up to there. Every point that you plotted, you go up 2 more. That's your called a vertical shift. By shifting the graph of f of x equal x squared up 2 units, the entire graph, you get the u graph. And that's what you got. Now, most of the time when you got this graph, you picked points and you plotted them. So every time you had a plot, do here. This was 1, 1, so it's 1, 3. This is negative 1, 1, negative 1, 3. So you just shift everything up 2 units. Okay? Now, in function notation, h and f are related. They're third cousins. Okay? Now, h of x is equal to x squared plus 2. Well, x squared was your f of x, that's your parent function, plus 2. So the parent function, the y value plus 2. Shifting it up 2. All right. Now, what happens if you do this, though? G of x is x minus 2 squared. What's your parent function? Same one, the squaring function. But what have you done here? Yes, you shifted the x. But which way did you shift it? To the right. A plus here means up. A minus here means right. When you're dealing with the x, everything seems backward. Okay? This is a shift to the right. Now, how you can tell that, plug in a 2 there, and you get a 0. That 0 is shifted to the right, too. So, yeah, you did shift to the right, too. Every point you did. 1, 1 became 3, 1. Negative 1, 1 became 1, 1. Everything shifted to the right, 3. You changed your x, kept the y. On the previous one, you kept the x and shifted the y. Okay, so that's right 2 units. So remember that. A shift on a vertical shift, go the direction the sign tells you. Up is positive, down is negative. For a horizontal shift, the sign here being negative, you shift to the right. The sign, if that had been a plus, you shift to the left. Just weird the way x's are backwards. Okay? Any questions on that? All right. In this case, the functions g and f have the following relationship, that g of x is x minus 2 squared, which is f, which is your parent function of x minus 2. Okay? I don't see anything new there, but that is a shift of 2 units. To the right, because anything you're dealing with the x, you go in the opposite direction. The following list summarizes this discussion of horizontal and vertical shifts. Okay? If c is any positive real number, okay? C is a positive real number. Vertical and horizontal shifts of the graphs f of x are represented as follows. What is this one? Up. Vertical shift up. Vertical shift down, C units. Right, C units. Left, C units. Okay? Very good. Horizontal shift, left, C units. Does that make sense? Okay? If you do it to the function, you go up or down. If you do it to the x, you go right or left, horizontal. Because the vertical, your y's are up and down, and your x's are left and right. Some graphs can be obtained from combinations of vertical and horizontal shifts, as demonstrated in example 1b. Well, what did they just do? They skipped example 1. What a good, clever thing to do. Okay? So let's do example 1 now. Use the graph of f of x equal to x cubed to sketch the graph of each function. So let me get my pen activated here. So f of x is equal to x cubed. That's your parent function, the cubic function. And your a part here, so, and let's go on and draw the graph, okay? Give me a few points for that cubic function. Yeah, f of x equal x cubed. 0, 0, got it. Let me tick off a few points here. That means make them mad, okay? Okay. 1, 1. Negative 1, negative 1. 2, 8. 1, 2, 3, 4, 5, 6. I'm off scale already. And negative 2, negative 8. Okay. So it does something like this, flattens out here, and then takes off. That's pretty ugly, but there it is. Okay. So there's our parent function. Okay. What color do you want G to be? You get to choose.
Green.
Green. Light or dark? Dark. All right. I like it. Okay. Here's your G of x is x cubed minus 1. How do we graph that one? Say again? Down 1. So that one goes there, that one goes there, this one goes here. We're off scale, so it goes something like this. There you have it. Pretty easy to do, right? Okay. How about my B part? What color you want it? Red. Red. Okay. They are calling it orange, but that's okay. Here's the B part. And it is x plus 2 cubed plus 1. What is h of x? H of x is equal to x plus 2 cubed plus 1. What in the world is going on there? Second? Left 2 from your parent function and up 1. Okay, so there it will begin there. This one will go left 2 and up 1. This one will go left 2 and up 1. And there, this function will be something like that. There you have it. You did a horizontal shift here, left 2, vertical shift up 1. Does that make sense? Every point, 0, 0, went left 2 and up 1. Negative 1, negative 1, went left 2 and up 1. Positive 1, positive 1, went left 2 and up 1. Every one. I just didn't have any more on the graph, but there they went. Left 2, up 1. Mine don't look very parallel, but, and they're not quite, but if you look at your graph in the book, you'll see those. There is a checkpoint there, well worth your effort to do that one. Okay, so that was our shifting graphs. Any question on that? Okay. So vertical and horizontal shifts generate a family of functions, each with the same shape, but different locations on the plane. If you had looked at mine, that cubic function is shaped exactly the same no matter where we put it. Okay? That means we call them rigid functions. It doesn't change shape, it just changes its position on the graph. Okay? Here we are. Goodness gracious, why did they put them in the other order? Okay? Don't know why it's out of order. So here, what we've already done this. Let's see how they did it. There's your first one. Okay? They plotted your parent function, f of x equal x cubed. Then they dropped it down by 1, and there you have the same shape, just depressed by 1. And then for the second one, same shape, but left 2 and up 1. And sure enough, identical shape to this one. It's a rigid transformation just with left 2 and left 1. Make sense? All right. Any questions? Sorry, they got the slides out of order, it looked like. And there that one is again. Isn't that the same? Some graphs can be obtained. Oh, they almost say the same thing in 2 places. Okay, that's what threw me off. So they have them in the right place. Okay. In example 1b, you obtain the same result when the vertical shift precedes the horizontal shift. It doesn't matter on the order, or when the horizontal shift precedes the vertical shift. Okay? Now, when you start reflecting graphs, though, I kind of like to reflect first and then shift. They'll say it doesn't matter, but I think it usually serves you the better stead to do that. So what do we mean by another kind of reflection? Again, it's a rigid thing, but now it's changing its direction. For example, if you consider the x-axis to be a mirror, here's your f of x equal x squared. There's your parent function. If it's minus x squared, you're negating everything here, so everything just gets flipped across, reflected across the x-axis. Right? 0 stays 0, negative 0 is negative 0. But plus 1 becomes minus 1. Minus plus 1 becomes minus 1. Everything gets negated, which means flipped across the x-axis. Okay? It's a mirror image or reflection of the graph f of x equals x squared. So that's a reflection across the x-axis. What do you reckon a reflection across the y-axis would be? This is negating the y, right? F of x equals y. That would be negating the x. Okay? They're not, well, here they say reflections across the coordinate axis. Reflections of the coordinate axis y is equal f of x are represented as follows. Reflection across the x-axis, you negate the y. That flips it under. If you're reflecting across the y-axis, you negate the x. Okay? That reflects it across the y-axis. Now that last one we did, if you put a minus x in there, minus x squared is the same as x squared. So negative x parentheses squared, and that just does that. It looks identically the same. So that reflection doesn't give you any difference at all. Okay? That's why I wish they had shown you one with a vertical reflection or reflection across the y-axis. They didn't show one, but you can imagine it. All right. Now, here we're, example 2 is writing equations from graphs, okay? They're not quite doing it, but they're showing it. They're showing you the function, and then they're showing you the graph. Now, what they should be doing is showing the graph and saying, what function is that? Okay. But they're showing you how to do it first. How do we do this graph? What does that look a lot like? It looks like a quadratic. And guess what? Every even power will look like that quadratic. Okay? But here's the difference. Whereas a quadratic comes down and just kisses the x-axis there and goes up, this one comes down and lingers a bit longer. So it's flatter around 0, but steeper over here. Because if you think about a quadratic, it goes up pretty slowly. This one, once it gets over this long linger, then it goes almost straight up, not straight up, but it goes up much more sharply. If you think about that, 1, 1 is there, negative 1, 1 is there. Okay, but in a quadratic, 2 would be 4. For this one, 2 would become 16. So it goes up quite a bit faster. Okay. So with the first one given in mind, there's your f of x equal x fourth. That's a new parent function, okay? Now, write the equation for each of these functions. What would be g of x here?
G of x equals negative x
Negative x4, because you flipped it over,
plus 2.
plus 2, you went up to. Very good. How about that one? It's negative. It would have been an x4, but then you have a minus 3. So it's x minus 3 to the fourth power. Negative on the outside, x minus 3 to the fourth power. Okay? Let's see if we can get those written.
So when you flip it, it's make it negative. Can you put the negative sign outside the parentheses?
Okay, that's exactly right. Let me get my pen back to dark. And this would be g of x would equal, and what you said was minus x fourth. That flipped it across the x-axis, and then you added 2 to it. That one was pretty straightforward. This one, you would have had a minus x fourth, but you also shifted, so it's minus x minus 3 to the fourth. Okay, the horizontal shift, you have to do that to the x. Okay? But it's not to minus x, it's to the x. That takes it 3 places to the right, and then you flip that across the x-axis. So in this case, this one I like to flip first and then elevate. This one, probably better to shift first and then flip. Okay? It really works either way, but to get your thing. Is everybody seeing that, by the way, h of x? You see how we got that? And there's your question about the minus sign? Yeah, it goes in front. If you have parentheses in front of the parentheses, no parentheses, it goes there. But remember what this means. You raise that to the fourth power before you negate. Please excuse my dear Aunt Sally. Okay. All right. So A is G is a reflection, and then a negation. And a shift. So that would be minus x fourth plus 2. Very good. The B part, you had a horizontal shift 3 units to the right, so that'd be x minus 3 to the fourth, but then you had a reflection, which made it minus x minus 3 to the fourth. All right. We will pick up on that slide next time. Actually, we will pick up on example 3 next time. They skipped example 3, which is a huge shame, because that's a far more complicated problem than what we had otherwise. All right, and I've lost my piece of paper I've been marking my place with. Let me give you a few homework exercises, and we almost finished 1-7, by the way. You can do either 5 or 7 or both. Do number 9, and do 11 or 13 or both. And I think you can probably do any of the odds 15 through 19 as well. I think you can probably do any of the odds 21 to 45 as well. And I think you can do any of the odds 47 to 53 as well. I think you can do 55 or 57. I think you can do 59 or any of the odds 59 to 63. But hang on there, we'll do the rest of those later. Okay, you folks who didn't get a quiz, but you gotta get your graph paper, hang on, let me go get 9 more copies made, and I'll be right back. Let me